All right. Sorry about this. I just totally tweaked my back. I don't even know how it happened really, and was laid up on the couch all weekend. So I felt like I needed to do one more day before I was fully standing up and driving and all of that. So I should be back just fine for Wednesday on when we're going to be doing review for the exam. So, like I mentioned in the email, just remember we've got review on Wednesday and then the exam on Friday, covering chapters 5 and 6. Okay, so some of my classes were able to do this problem, others didn't quite get to it. So, I'm going to go ahead and do that here. And if you have already done it, then just feel free to skip ahead in the video. Okay. So this is, looks like a pretty complicated question, but we just basically need to isolate, the same thing we've always done is that we're going to have a mole to mole conversion in the middle. And the reason I know that is because first I have a balanced chemical equation, so that's a good hint. And then also it's giving me information about NO and about this compound urea, CONH2. So we're talking about two different chemicals, and anytime we have the two different chemicals, we're going to be doing that mole to mole conversion. So now we have to figure out like what's going to be on the beginning side and what's going to be on the end side. And if you look at it, you're given a pressure, temperature, and volume for the first compound, and then you're also given a pressure and temperature for the second. So using PV equals nRT, we need 3 of those 4 variables in order to find something else. So sorry about that. I have 3 for the NO, but I only have 2 for the urea. So that's how I know that I'm going to have to be starting with the NO. So I'm going to be using P, V, and T to get me to, this is of NO, to get me to moles of NO. Then I'm going to convert to moles of urea. And then at that point, I have N, and so I can use P and T to get me to volume, which is what they're looking for. What volume in liters? Okay, so PV equals nRT to get me to moles of NO, the mole to mole ratio to get me to moles of urea, and then moles, pressure, and temperature to get me to volume of urea. Okay, that's where I'm headed. So although we usually do these calculations as one big long one, other times here, since we're using an equation for the first and last part, they're going to be broken out into 3 separate things. So I like to rearrange my equations first before I put any numbers in. You don't necessarily have to do it that way. That's just my preference. So I'm going to divide both sides by RT to isolate N. So I get PV over RT. And I'm going to have to plug in these values. Now, the NO is given in torr. So I do need to divide by 760 torr to get that into atmospheres. Okay, so let me just do that real quick. So this is 0.0158 atmospheres. And my temperature's already in Kelvin, my volume's already in liters, so I should be good to go. So pressure, 0.0158 atmospheres times the volume, 2.55 liters, over R, 0.08206, and temperature, 655. Okay, so my moles of NO comes out to be 7.49 times 10 to the negative 4th Yep. Oh, this reminds me. If you're in section B, the one that meets at 11 a.m., we did this problem, but I remember somebody brought it up at the end and I didn't see what was wrong, but we figured it out. So check your work in your notes, because there was a point where I had all the work, but then I plugged it into my calculator wrong. So like the final answer was wrong. I just don't want you to be confused about maybe why you got a different answer. Okay. All right. So this is moles of NO. So now we're going to use the balanced equation and we're going to take moles of NO and we're going to convert that. Get that balanced equation out. 4 moles of NO for every 2 moles of urea. So 4 moles NO, 2 moles of CO, and H2, 2. Okay, from our balanced equation. So I think if I remember right, this is where I wrote something down wrong for the calculation. I think I multiplied by 4 and divided by 2, something like that. So 3.75 times 10 to the negative 4th, 2, 3, 4, yep. Okay, and now that is moles of, I'm just going to write urea because it's easier. And then we need to finally solve for volume. So again, we're going to do PV equals nRT. Here we have N and we're trying to solve for V. So I'm going to rearrange that equation as nRT over P and plug everything in. So 3.75 times 10 to the negative 4th moles, 0.08206, temperature 298 Kelvin, and pressure 0.993 atmospheres. Okay, and this is going to tell me the volume in liters of urea that was produced from this pressure, temperature, and volume of NO. Okay, so this volume comes out to be, let's see, 9.22 times 10 to the negative 3rd, or, and this is in liters, or we could write this as 9.22 milliliters. Okay. All right, we will come back to this problem in a minute, probably. Maybe I'll leave it for review on Wednesday. We'll see. But we haven't done enough about partial pressures yet. Okay, so maybe like 2, sort of 3 big ideas in this last section. So the first one is we very often will measure gases at... it's funny, I was about to say like a standard typical conditions, but the conditions are actually 0 degrees Celsius here, not room temperature. So maybe it's not that standard. But we've set up a pressure and temperature that we consider the standard so that we can bring gases to this pressure and temperature and easily be able to measure their moles and volume or equate their moles and volume. So the pressure that's been dictated is 1 atmosphere or typical atmospheric pressure. And the temperature that has been defined is 0 degrees Celsius or 273 Kelvin. Okay. Now, for any mole of gas, it doesn't matter what the type of gas it is, for any 1 mole of gas at standard temperature and pressure, the volume that we would calculate from PV equals nRT is 22.4. So why is this so interesting? It's because, it's not so interesting really, but why is it so useful? It's because we can utilize the fact that it's 22.4 liters per mole of gas as, you guessed it, a conversion factor. So this is only applicable if we're at standard temperature and pressure conditions. It's really just a shortcut. If you were given the conditions of 1 atmosphere and 0 degrees Celsius, you could always just plug into your regular equations and not have to worry about it. So that's kind of one way you can approach this, is just know that STP means 1 atmosphere of pressure and 0 degrees Celsius or 273 Kelvin, and then just plug in the numbers like normal and kind of don't worry about remembering that the volume of 1 mole of gas at STP is 22.4. Or you can remember that value. So, here's just kind of like a visual description of the fact that if we have 1 mole of gas, it doesn't matter what the gas is, if we have 1 mole of gas at standard temperature and pressure, there will always have a volume of 22.4. So we call this the molar volume, or the volume of 1 mole of gas at these set standard conditions. Okay, so anytime you have a problem that says at STP, just remind yourself that this is 273 Kelvin and 1 atmosphere of pressure. Okay, that's our kind of first big idea from today's material. The second one is the idea of partial pressures. And I know this slide probably looks a little bit intimidating with all of this kind of breakdown stuff. I would say in general, all you really need to take from this is the first part, which tells you that the overall total pressure is the sum of all of the individual pressures of a gas that is in some mixture. So the best example of this is just normal breathable air is a mixture of a bunch of different gases. So we've included all the, the gases that are the major components of air and the individual pressures that they contribute. Now, this one's given in percentage. Usually we're going to do that in pressure. So, for example, if we had 1 atmosphere, typical atmospheric pressure, we could now say that 0.78 atmospheres comes from the nitrogen and 0.21 atmospheres comes from the oxygen. So you see, I'm just moving these percentages into decimal form. And then the argon would be 0.009 atmospheres, and the CO2 would be 0.0004 atmospheres. Now, these don't add up to 100 perfectly. Well, I guess they're pretty darn close, actually, now that I look at it. Yeah, they're pretty darn close. So the total pressure is 1 atmosphere, and the individual pressures all add up to give you that 1 atmosphere. So that's what this equation is saying. Really, why this happens is kind of maybe obvious, but the point is they don't interact with each other. The gases don't interact with each other. They behave kind of independently of each other as far as how they contribute to the pressure. Okay, so we're going to use a couple applications of this. The first one we're going to do here is basically just utilize the fact that that we have this partial pressure equation that allows us to calculate individual pressures independent of each other, as well as the overall pressure. And then the last thing that we're going to do is talk about how this contributes to experimental techniques where we collect a gas over water. And the reason why that one's important is because we'll be measuring a total pressure, but that total pressure is going to be the sum of the gas and the water. So if we want to know the gas, we're going to have to subtract off the pressure of the water. So P gas will ultimately be equal to the total pressure that's measured minus the pressure of the water. So we'll get to that in just a second. Okay, I can tell already I'm going to need additional room for this one, so maybe I can just scroll up to the blank slide to do this. All right, let's just look at this individual gases first, and then we'll talk about the water one. So in this example, we've got 3 gases that are completely separated from each other, and they're closed off by these valves. And we're given a pressure and temperature of each one. And then we're going to open up those valves and allow the gases to mix. Okay, so we allow all these gases to fill into all of these individual containers. And the question asks us, calculate the pressure of CO2 after those, they're called stopcocks, these valves, after those are opened. Okay, and then we actually, I feel like in the past I've had this calculate each one independently and then add them together. I'm not sure why I didn't have that in this question, but maybe we'll go ahead and do that just because we have time, in the sense that you guys can work this on your own and you might have a little bit more time to do the calculations. Okay, so calculate the pressure of CO2. So really what we're saying is that CO2 initially accommodates this 1.50 liter volume, but eventually it's going to fill into this whole thing in here, which we need to think about what that total volume is. So if we have individual volumes for each of them, if we wanted to look at the total volume, we should just add those together. So 1.5, 2.5, 4.5 liters is the total volume of these gases. So if we just want to know the pressure of CO2, we don't have to consider the fact that all those other gases are in there. And this is kind of where the application of it's Dalton that came up with this law of partial pressures. But this is where that comes into play, is what we're saying is that we don't have to consider the other pressures of the other gases. We can just pretend like CO2 is in there by itself. Okay? So this really is just a P1V1 equals P2V2 problem. It's just that those pressures and volumes are only for the CO2. We're not going to worry about the fact that there's hydrogen and argon mixed in there as well. Okay? So I'm going to plug in the initial ones, pressure of 2.13 atmospheres and volume of 1.5 liters. And my new pressure and the total volume once I open those valves, 4.50 liters. Okay, so that pressure 2, so this is just of the CO2, is going to be 2.13 times 1.5 divided by 4.5, or 0.71 atmospheres. Okay, so this is the individual pressure of CO2. Now, we could go ahead, and maybe I'll do that on this blank slide up here. We could go ahead and do the same thing for the hydrogen and for the argon. And then if we wanted to know the total pressure once those valves had been opened, we would just add them together. Okay? So I'm going to go ahead, and I might have to switch back and forth a little bit to look up these numbers, but I'm going to go ahead and do the same thing to find the new pressure of each of these gases once those valves are opened up. So I realize the question doesn't actually ask this, but I'm adding this in. So let me rewrite it up here. So we calculated that the pressure of CO2, and now we want to do the pressure of H2 and the pressure of argon. So calculate the new pressure after the valves are opened of CO2, which we already did, argon, and helium. And then we're going to say calculate the total pressure. Okay, so we already did CO2. That was 0.71 atmospheres. And I just saw it's not helium, it's hydrogen. Okay. The pressure of argon, again, for each of these, we're doing the new pressure, pressure 2 of argon is going to be P1 V1 over P2. Sorry, over V2. Oh, I hate when that happens. Oh no, it just zoomed in. I thought it like erased it. Okay. And then the pressure 2 of hydrogen is going to be P1 V1 over V2. Now, if you're getting at all confused, you could write these a little more specifically. You could say P1 of argon, V1 of argon, and then V2 is the same number for all of them because that's just that 4.5 liters, the total volume once we open those valves. Okay, and then the total pressure is going to be the pressure of CO2 plus the pressure of argon plus the pressure of H2. Okay, so for argon, the initial pressure and volume, 1.15 and 2 liters. And like we said, the total volume is the same for all of these, 4.5 liters. Never seem to leave enough room. Okay. So this one is 0.51 atmospheres. And then for hydrogen, 0.861 and 1 liter. 0.861, 1 liter over a new volume, 4.5 liters. Or 0.19 atmospheres. Okay, so our total pressure utilizing, so the first part is knowing that the gases aren't going to be interacting with each other, and so we can treat them separately and just do a P1 V1 equals P2 V2 for each individual gas, and then the total pressure, we can just add those together. So 0.71 plus 0.51 plus 0.19 for a new total pressure of 1.41 atmospheres. So the whole pressure in that container is going to be 1.41 atmospheres coming from CO2 contributing 0.71, argon contributing 0.51, and hydrogen contributing 0.19. So that is a good, relatively complicated application of Dalton's law of partial pressures. Now, the other good, like I said, the good application of Dalton's law is when we do an experiment, we often collect gases over water. And this is because it's just an easy way to trap those gases. And then we go ahead and measure the pressure that's produced. So we're measuring the pressure in this area. The problem is some of that was the gas that we produced in the reaction, And some of it is just the fact that water molecules are going to evaporate anywhere where they are in a closed system. So if you have a container and you put a lid on it, there will always be a small amount of water particles that are in what we call that head space, like the spot above the liquid up to the cap. There's always going to be a little bit of water molecules in there. So if we measure what I've highlighted in this area here, if we measure that pressure, so I'm going to say P total or P measured, that isn't really the pressure of the gas that we've produced. It's the pressure of the gas plus the pressure of the water. And we don't really want to know the pressure of the water. We just want to know the pressure of the gas that was produced. So the way that we're going to do that is use Dalton's law of partial pressures to know that we can just subtract off the pressure of the water, and that will tell us the pressure of the gas that was produced in this chemical reaction. Okay, the one little bit complicated thing is that the pressure of the water changes with temperature. And this shouldn't be that surprising because as you warm water up, more and more of it evaporates until eventually you reach the boiling point of water, 100 degrees Celsius, and then all of it can evaporate. Okay, so the lower our temperature is, the more water is going to go into the vapor phase and create these little water molecules up in that headspace. Okay, so let's see an application of this. All right, we have hydrogen gas collected over water. So that's the key phrase you're looking for, collected over water. This is just like the picture we had where we have hydrogen gas that is a consequence of mixing zinc and HCl. This is a great example from chapter 2. So this is a metal plus an acid. This is a gas evolving reaction. Okay, so hydrogen gas gets produced and then zinc chloride gets left behind. So again, a gas evolving reaction that is happening in an aqueous solution, because this one would be aqueous and this would be solid. Gas would be produced and you'd have this aqueous zinc chloride left over. How do I know that it was aqueous? Because all chlorines are soluble except for silver, mercury, thallium, and lead. So zinc chloride would be soluble according to the solubility rules. That was a fun little sidetrack. Okay. Then it also says calculate the pressure of dry H2. It means, and it says that there, I won't always tell you that, but it says without the water contribution to the pressure. So it means that you need to subtract off that water. So the pressure that's measured, P total, is 750 torr. But remember, that is the pressure of the hydrogen plus the pressure of the water. So if we want to find the pressure of the hydrogen, we need to take that 750 torr and subtract the pressure of the water. And the way we find the pressure of the water is by looking at that table at that particular temperature. So 25 degrees Celsius has a pressure of 23.48. So it's a pretty small contribution, which should make sense because there's just a small amount of water that's evaporating. So the pressure of the hydrogen itself is just 726.52 torr. So that's the pressure of the hydrogen gas. So this said calculate the pressure of hydrogen. That's all we have to do. We don't actually even need this volume there. Now, it could take it one step further and say calculate the moles of hydrogen. because at this point, we have temperature, we have volume, and we now have pressure of H2. So we could actually go ahead and calculate the moles if we wanted to, which is good because in a chemical reaction, that's often what we're wondering about. All right. Okay, last thing we need to talk about in chapter 6 is just a concept thing, and to clarify why we call PV equals nRT the ideal gas law. So there are a couple assumptions that are made when we talk about the ideal gas law. And those assumptions are summarized in a theory called kinetic molecular theory. So this is like what the assumptions are that we're making. Some of the assumptions are pretty good. Some of them are maybe not quite as good, and they have an effect on the accuracy of using PV equals nRT. So the assumptions that are made, the size of the gas particles are assumed to be 0. Okay, that's kind of bizarre, right? We're saying that, like, let's look at that picture of hydrogen gas. We're saying that these particles, their volume doesn't contribute. Now, the reason why that's very often okay is because they are very small compared to the total volume. And because there's so much empty space, the total volume of each of these individual particles is not going to be a big contributor to the overall volume. So like, let's say that this was, let's say that this container area was like, I don't know, 200 milliliters. Maybe the gases contribute like 0.05 milliliters, but that's not a big contribution. If we assume that the volume of the container is 200 milliliters, even if the gas particles contributed 0.05 milliliters, that's not that different. The volume then left over would be like 199.95, which is not that different. So that's usually a pretty good assumption. So sometimes, though, if the particles are particularly large, this might not be a good assumption. And down here is we have a list of when these are good assumptions. So if we had really big particles, then number 1 would not be a good assumption. So if we have small particles, we're saying it is more likely that PV equals nRT is going to be accurate. So again, just to kind of restate, these are the assumptions that are made that allow us to assume that PV equals nRT is always right. And if these properties are true, then PV equals nRT is relatively accurate. If we diverge from these properties, then they behave as what we call real gases, or another way of saying that is that PV equals nRT is not particularly accurate. So this would be if there are large particles, then PV equals nRT would not be particularly accurate. Now we have some pretty complicated equations that allow us to calculate what the pressures or volumes or whatever of a gas would be, if PV equals nRT isn't accurate, but that's more than we need to go into today, or in this class for that matter. Okay, other properties. The average kinetic energy is proportional to the temperature in Kelvin. This is a pretty good assumption. We know that Kelvin is a good measure of kinetic energy. Okay, so as long as we're at relatively high temperatures, this is a really good assumption. So if we were at very low temps, I'm going to put very, then PV equals nRT would probably not be particularly accurate. And then finally, number 3, the collision of particles. So particles hit the wall, they hit each other. We're going to assume that they don't attract to each other in any way when they bump into each other. They just hit each other and then they move away, not being attracted to the other particle at all. Now, this is fine if we have a small amount of gas in our particular volume. This is because those gases don't have to bump into each other nearly as much. And when they do bump into each other, they kind of have a little more room to dissipate any of that energy associated with the collision. Okay, so these are our 3 assumptions that we make to be allowed to use PV equals nRT. These are good when the particles are small, when they're at high temperatures, and when they're at relatively low pressures. If we were to have the opposite conditions, where we had big particles, or we had really low temperatures, or we had a lot of gas in a small amount of volume, which another way of saying that is a high pressure, any of those things, we would label these as real gases, and it would require us to do some additional calculations because PV equals nRT would not be particularly accurate with these conditions. Okay? All right, so that's the end of chapter 6. The chapter 6 homework, don't forget, is due Wednesday before class. That'll be a good chance for you to see kind of how comfortable you are with the chapters and with the types of problems that you're going to be asked to do, both math and concept. So I tried to include, both types of questions in the practice problems. So, sorry, I was talking about the homework first. So that one's due on Wednesday. The optional practice problems are obviously for you to use in your studying. And no, they do not get included in your grade. I know sometimes in Pearson it looks like they do. They don't, I promise. So you can use those either before coming to class on Wednesday so that you can ask questions about them, or maybe we'll do some of them together and then you could finish them off on Wednesday night and Thursday as you're studying for the test, just to make sure you feel comfortable actually approaching these problems. So I can't emphasize enough that practice is what's going to help you to be able to know whether or not you are comfortable enough with these types of calculations. Don't just assume like, oh, I understood her when we talked about it in class, I'll probably be fine. Now, if you understood me and then you did the homework and didn't need a whole lot of help from your textbook or from, the internet, then you're probably fine. But if you struggled with the homework a bit, you struggled with understanding the material in lecture, what you probably need to do is use the homework more as a study tool and utilize the textbook and the online material to use that as a way to get familiar with the types of questions you're going to have, and then use the practice problems as a way to reassure yourself that you can do those without the additional help. Okay? I'll be around all day. I'm just going to be trying to lay on the heating pad most of the day, so feel free to send me emails. I'm happy to answer any questions. Okay? I'll see you guys on Wednesday.